Welcome back to the deep dive. Today we are taking a really deep plunge into a set of documents all about a tool called Flow.
Right. It's a visual automation tool for embedded devices.
And this isn't just about, reading the manual.
Yeah.
We want to give you a shortcut to understanding how you can deploy some extremely complex, customized logic.
And without ever compiling a single line of code.
That's the promise, isn't it? The whole no-code thing.
It is. And our mission today is to decode its visual language and really get into the surprising depth of the logic that's available in this builder.
So if you've ever wanted to turn a simple event into some sophisticated timed sequence that talks to other systems, this is for you.
I love that. It really just pulls the complexity out of the equation.
It does. You drag nodes, you wire them up, you can listen for access events in real time.
Apply logic. Call HTTP endpoints. It's a moving device programming from, some obscure text file to what's basically an interactive whiteboard.
Yeah, but what's really fascinating here is that it's not just a pretty front end.
No, not at all. It's a purpose-built execution environment. It uses color, shape, even animation to show you the state of your automation.
It's its own live debugger.
Exactly.
Okay, so let you unpack this. Let's start with the environment itself, the Flow builder.
You launch it right from the app's UI, and when you're on that canvas, pretty much everything revolves around the floating action bar.
That bar is essential, isn't it? It dictates the whole mode of operation.
It really does. The crucial button there is Start-Stop Execution. When you hit Start, two things happen right away.
Okay.
First, editing locks. And second, the whole graph switches into what they call live mode.
Which means your automation is now actually running on the device.
It's live.
And the visual feedback you get in live mode is fantastic for anyone learning this.
Oh, it's huge. If your logic is executing, you immediately see the little edges between the nodes start to animate.
Showing the direction of the signal flow.
Yep. And the data values themselves, they glow. This is instant visual debugging.
So like a Boolean value, a simple true false.
Will glow bright green for true or bright red for false. You know instantly if a sensor is triggered or if a logic gate is active.
And stopping the flow.
That automatically saves the entire graph, so you never lose your work when you pop out of live mode.
That's good fail-safe. Okay, let's zoom in on the core language here, the wiring.
This is where the docs show a really elegant system for managing data types.
I noticed the handles, the connection points, they're always outputs on the right, inputs on the left.
Right, but the shape coding is what really stops you from making errors before they happen.
The shape tells you the data type.
Exactly. A round handle is a Boolean. A square is for numbers, integers, floats, both. And a diamond shape means the data is a string, text.
So if I try to connect a round Boolean output to a square numeric input, the system should just stop me.
It won't let you. It enforces that type consistency visually.
And those shapes get colors in live mode.
They do, which helps so much when you're tracing a complex flow. Booleans are green-red, integers are magenta, floats are purple, and strings are the cyan color.
And the line connecting them just mirrors the color of the source.
Mirrors the source output color.
That is genuinely smart. It's a whole visual vocabulary.
It is.
Okay, before we leave the interface, what about node customization and warnings?
Well, you can click any node to open a drawer on the right side. You can rename things, change the header color just for organization.
But there's a more critical visual cue.
Right. Yes, the orange dotted border. If you see that on a node, Flow is basically yelling at you that you've missed some required configuration.
So like an HTTP node needs a URL or a timer needs a duration.
Exactly. You can't trust that flow to run correctly until every single one of those orange borders is gone.
It's like a visual checklist.
That's a great way to put it. It forces you to complete the setup.
So we've built the container, we understand the canvas, now we have to connect this thing to the actual device, the sensors, the actuators.
This is where Flow becomes the brain of the machine. We're moving from the abstract canvas to the hardware reality.
And the core connection points are the access metadata events.
Right. You have the subscribe node. That turns your flow into a listener. It hooks into these rich real-time events.
Things like what occupancy counts from an analytic or license plate reads?
Exactly, or object classification. It then just exposes those data fields as outputs you can immediately use in your logic.
And on the flip side, Flow can actually create events, can't it?
It can. The access metadata event create node lets your flow define and publish its own custom event.
Which sounds powerful.
It is powerful, but it comes with a really crucial warning that the documentation hammers home.
Okay.
These custom events are only visible in the access event rule list while your flow is actively running.
So you stop the execution.
And the definition of that custom event just vanishes from the system.
That makes sense. The flow is the event, so if the flow dies, the event source dies with it. So how does it talk to physical outputs? Relays, ports.
That's the Access Outputs node. It uses VAPX, which is Access's own API, to toggle those physical ports.
Is there a trick to that?
There is. A key piece of operational knowledge here is that if you ever change device credentials, the IP or the port mapping in the device settings,
You have to update the node.
you have to literally delete and recreate that Access Outputs node and flow. It needs to refresh its connection details.
That is a great tip. And I see there's also an Access Livestream node.
Yeah, that's just for on-the-fly verification. It gives you an RTSP video preview, which is so useful for confirming that the detection logic you just built is actually triggering when it's supposed to.
Right. Okay, now let's pivot to what seems like the most sophisticated part of flow.
The industrial logic building blocks.
This is where it really separates itself, right? It's offering things you'd normally only find in, like PLC programming.
Dedicated PLC programming, exactly.
So let's start with a classic one, filtering noise. The debounce node. Why do we need this?
You need debounce anytime you're dealing with a noisy input, especially from a physical sensor. Imagine a door contact that chatters. It flickers true, false really fast when a door closes.
Instead of one clean signal.
Right. And if your flow reacts to every single one of those flickers, you'll end up firing, 50 pointless network requests.
The debounce is a stability filter.
That's it. It only lets the Boolean change pass through after the input has been stable at that new value for a set amount of time. It just smooths out noisy inputs.
Okay, that makes perfect sense. But the section that really needs some clarity is the three timers. TON, TOF, and TP. Why three?
Because they solve three fundamentally different automation problems. We can use some simple analogies to make it stick.
Please lay them out for us.
Okay, first up is TON, the timer on delay. Think of this as a mandatory waiting period before something happens.
Okay.
The output goes true only after the enable input has stayed true for the full time you set. If enable drops early, the timer just resets.
So you'd use this if you need a motor to spin up for 5 seconds before the next step in a sequence can start.
Perfect example, delay before starting.
So what about TOF, timer off delay?
TOF is the exact opposite. It gives you a coast or a hold period after the trigger is gone.
How does that work?
The output goes true instantly when it's enabled. But when the enable input drops to false, the output stays true for the set time.
Like a bathroom light on a motion sensor, it stays on for a minute after you've left.
That is the perfect analogy. It's holding the state.
Which leaves the pulse timer, TP.
TP is for momentary actions. It just generates a single fixed-length pulse.
When?
Every time the enable input goes from false to true, that's called the rising edge. It doesn't care if the input stays true for an hour. It just fires one quick, say, 2-second pulse.
Useful for triggering a momentary switch, like a door strike.
Exactly, a single quick action.
Having those three tools gives you incredibly fine-tuned control over sequencing, which I guess leads us to the sequencer nodes.
Yep, you have the step sequencer for discrete processes. It advances one output every time it gets a pulse.
And crucially, exactly one of its outputs is true at any given time. Perfect for managing phases of a process.
And then you have the time sequencer for more continuous cyclical jobs. It runs its internal timers in order, and when the last one finishes, it just wraps back to the beginning.
Like cyclical pump operations or rotating digital signs.
You got it. It just runs continuously while enabled.
Okay, this is where it gets really interesting for me. Handling data and making complex routing decisions. We need to go beyond simple and/or gates.
Oh, absolutely. The compare node is a real standout here. It's not just for numbers.
Right, you can use it for strings.
You can configure it for really detailed string operations, like checking if a text input contains a certain word, or if a file path starts with a specific folder name.
You just set the operator and the data type, and it makes the decision.
And then there's the flip-flop node, the classic latch that holds a state until it's reset.
And the documentation makes a big deal about the choice between RS and SR modes. Reset dominant versus set dominant. Why does that matter in practice?
It matters for safety and for priority. In RS, or reset dominant mode, if both the set and reset signals arrive at the exact same instant.
Reset wins.
Reset always wins. This is critical if your reset input is tied to, say, a safety shutdown. You always want the shutdown to override a simultaneous command to start something.
So it gives the logic a clear hierarchy. For safety, you pick RS mode.
Precisely. Now, for just routing data, you have two key tools,
The value selector.
That's the simple one. It just uses a Boolean input to switch between two different value inputs, a simple A or B switch.
But the multiplexer is way more powerful. It can route one of many inputs based on a numeric index.
Right, so imagine you combine a four-step sequencer with a multiplexer. The sequencer's output 1, 2, 3, or 4 can feed the multiplexer's index.
And that lets the flow pull the correct sensor reading or preset value that matches the current step of the process.
You see how it all starts to connect together?
Yeah, I do. Flow also handles temporary data storage. We saw FIFO and LIFO queues. What's a quick scenario for needing a queue on a device?
You might use a FIFO, first in, first out queue to store license plates detected during rush hour.
So even if the flow gets bogged down, processing HTTP requests.
The queue makes sure every single plate that was detected is buffered in the order it arrived, so you don't lose any data until the processing catches up.
It handles burst data gracefully.
Exactly. And for something more stable, the data table is just a straightforward register block, a place to hold values that lots of different parts of your flow might need to reference.
Like config parameters or running totals.
Simple as that.
Now for the final, and maybe most important, piece, networking. How does Flow turn this device into a robust network player with the HTTP request node?
Well, it is extremely robust. When it's triggered, it fires off a request and gives you immediate outputs for success, status code, the body of the response, and any errors.
And the configurations look really comprehensive. You can set the method, the URL.
And define all kinds of body types: raw data, XML, form data, structured JSON.
It even handles authentication. Not just basic, but digest auth too.
Which is necessary for some older or more secure systems, yeah. You can even tell it to skip TLS verification, though you use that setting with a lot of caution, obviously.
But the real game changer is how it processes the response it gets back.
Yes. The JSON key extractor is the essential partner to the HTTP request node.
This is the tool for parsing those complex data responses. Tell us about the dot notation it uses.
This is so important. An external API will often return a JSON object that's, deeply nested. So if the status you actually need is nested under data and then under current state, you don't have to write any code. The key extractor lets you just input the key path as data.currentstate.
And it just pulls that specific value out of the JSON string for you.
Automatically. It makes pulling relevant data from modern web services incredibly streamlined.
No custom parsing code at all.
None. It connects that high-level device automation directly to your enterprise systems.
Okay, that brings us to our final section, visualization and debugging. Since we're designing this all visually, we need good visual tools to confirm it's all working.
Verification is everything in a no-code world. The oscilloscope is probably my favorite here.
It's basically a logic analyzer inside the flow.
It is. You can plot up to 5 different signals, numeric or Boolean, in real time. It lets you visually confirm that your 3 different timers, the TON, TOF, and TP, are all firing in the exact sequence and for the exact duration you wanted.
You can set the line colors, the min-max ranges, and build your own little diagnostic dashboard right there on the canvas.
You can. The speedometer is another one. Gives you a gauge for a numeric value. Great for monitoring counts or system load.
And then there are the basic debug outputs for Booleans, strings, and the value debug output, which just gives you a little table of all the input states.
Yeah, all very useful.
Yeah.
But you mentioned an essential tip from the docs about debugging that we really need to emphasize again.
Right.
If you take away one single operational tip, it's this. Always include a logging node in your flow when you're testing.
Why is that so vital? The graph is already animated and live.
Because the animation shows you the logic executing, but the logging node shows you what's happening in the back end. When you're trying to figure out why an Axis event didn't trigger, or why an HTTP request failed with the timeout, the logging node is what outputs those critical back-end messages.
That's the stuff the visual graph can't see.
Exactly. It gives you the time, the error level, and the name of the node that created the message. It is your diagnostic lifeline to the actual device runtime.
This has been a really comprehensive look at flow.
I think so.
For the learner, the key benefit here is that this tool set gives you a complete, visually intuitive way to implement complex automation logic.
From industrial timing controls and priority latches to advanced networking and JSON parsing, it's all just abstracted onto this canvas.
The speed of development and just being able to verify your logic instantly with that live visual feedback, that feels like a game changer for custom deployments.
Absolutely.
So as we wrap up this deep dive, let's leave you with a provocative thought using all the power we've just discussed.
Oh.
Given the precision of that step sequencer, combined with the power of the networking nodes and the JSON key extractor's dot notation, what is the most complex, multi-step maintenance monitoring or reporting process that requires timing and external data retrieval that Flow could now automate entirely on the device, with no need for a separate server or an external program?
Think about fusing data from multiple sensors, timed reporting, and conditional actions based on what you pull from an external API. The possibilities are, well, pretty vast.
Think on that, and we'll catch you next time for another deep dive.